Good evening, everyone. My name is Badad, and I'm here to present an awesome slideshow on the topic of geophysical exploration in Middle East. First, let's go over some interesting statistics regarding the Middle East. Middle East covers 4.7% of the land area of the world, and it's home to 5.5% of the population of the world. But the most interesting thing about the Middle East is that it has a huge amount of oil reservoir in the world. By the current estimates, Middle East currently contains nearly 66% of the world's oil reservoirs, which is huge. Unfortunately, Middle East is not the most welcoming environment for geophysical exploration. It is covered by vast subgalt plains, which gives normal geophysicists a lot of headache with statics and numerous multiples. And then there are these soft sand dunes, which make it really hard for heavy machinery to transport. Then there comes these inaccessible jebels and mountains, which make it really fun for the geophysicists to plan their grades and start data acquisition. And let's not forget about the seasonally variable water table that goes up to 1 kilometer and the extreme temperatures in the summer and the winter. And of course, the exploration crew always has to look out for the sandstorms and those unforgiving winds that make it impossible to work. But what about the subsurface geology itself? We got karst terrain, we got extremely high velocity anhydrite layers, we got extremely low velocity unsaturated sands, and then we got cavernous holes that make it really hard to explore the subsurface. Now, to put these things into perspective, some of these fields are the size of small countries, and they push the boundary of our rock physics knowledge to unfamiliar territories where the conventional methods would fail outright in describing these fields. Now let's get to the more scientific part of this lecture as we try to describe the work of a group of geophysicists in an oil reservoir in Oman. Garif Reservoir is a huge oil reservoir in Oman which gave major headaches to geophysicists as they tried to characterize it. 3 wells were drilled into that formation and only one of them had a 10-meter thick sand layer. They all had a small net to gross ratios, and AVO modeling showed minimal difference in amplitude as the offset changed. It was found that the reservoir thickness is well below the seismic resolution, and so the top and the bottom are not really distinguishable, and therefore it was historically challenging to locate the channel sands, and therefore mainly grid drilling was used in Garif Reservoir. Therefore, geophysicists thought that by using high-tech solutions such as inversion techniques, they could overcome that problem and cut down on the production costs. However, previous studies showed that poor log and seismic quality, overburden effect, small seismic bandwidth, seismic multiples, and the close acoustic impedance of shale and sand makes it nearly impossible to invert the data properly. This group of geophysicists realized that if they remove the data from the part where shale washout happened, which is done using the caliper logs obtained through the well number 3, they can actually delineate sand from shale as it is seen in the second picture, where sand is shown with yellow and shale with color green. And so they found that the difference in AI is minimal, though the sand has lower VP over VS ratio and the wavelength in the soil is 10 times the thickness of sand. Therefore, they concluded that focusing on inversion is a distraction. And a synthetic model with 2 sand wedges was built which showed how amplitude and trace shape changes with sand thickness. As a result, an amplitude hotspot similar to the third well with good sand presence was predicted and drilled. Here you can see the synthetic model. Each sand layer in the middle of the model shows up as one reflector since their thickness is below vertical seismic resolution. However, the internal reflections show lateral variations from left to right. Barely any reflections are in the left of the model where NTG is 0. However, reflection is weak in the right of the model where NTG is 1 or close to 1. So well, synthetic data and real seismic data converge on one conclusion. The absence of thick sands eliminates the well-known tuning-related non-unique correlation between seismic amplitudes and sand thickness. This implies that tuning is actually a good thing, which means reservoir distribution in field Z becomes predictable and grid drilling is no longer needed. The picture on the left shows the location of the seismic hotspots where seismic characteristics are similar to well number 3. As a result, several other wells were drilled to confirm the boundary of this reservoir using amplitude which proved to be a huge success for PDL, and you can see this boundary on the right.
created using Powtoon.